In the previous video, we talked about the definition of a magnetic field. This video will show you how to use the magnetic field to calculate the magnetic force. As we've seen, magnetic fields differ from electric fields in several ways. One difference is that electric fields tell you the relative force that a magic proton feels. However, a magnetic field tells you the direction that a compass needle points. So we need an equation that relates the magnetic field to the magnetic force. Suppose you stood between the prongs of a very large magnet. The field would be roughly uniform. Let's analyze this field. The magnetic field is symbolized with the capital letter B. It's a vector, meaning it has direction. Magnetic fields are measured in a unit called teslas. To give you an idea of how large 1 tesla is, the magnetic field of the Earth is on the order of 5 times 10 to the negative 5 teslas. The powerful magnets used in MRI machines in hospitals might generate fields of 0.3 or 0.4 teslas. The equation that relates the magnetic field to the magnetic force on a particle is as follows. First, do the step in the parentheses. Take the cross product of the velocity of the particle and the magnetic field vector. Then, multiply that cross product by the charge of the particle. This yields the force on the particle. Before we go any further, let's revisit the cross product calculation. A cross product is an operation that is done on 2 vectors. For our purposes, we will always write these vectors in polar. The cross product operation produces another vector as its result. This means you have to find not only the size of the resulting vector, but also its direction. The size of the product is calculated like this. Take the size of the first vector, multiply it by the size of the second vector, and then multiply that by the sine of the angle between them. Now the direction. The direction is given by something called the right-hand rule. Take your right hand and line it up with the first vector. Bend your fingers so they are parallel to the second vector. Then extend your thumb. Your thumb points in the direction of the result vector. Let's see an example. Suppose the first vector, shown in green in the diagram, has a magnitude of 2 and lies along the positive x-axis. Thus, its orientation is 0 degrees. The second vector, shown here in blue, has a magnitude of 3 and is oriented along the positive y-axis. Thus, its orientation is 90 degrees. To begin, we'll solve for the size of the cross product. This is solved as the magnitude of the first vector, 2, multiplied by the magnitude of the second vector, 3, multiplied by the sine of the angle between them. That's 90 degrees minus 0 degrees, which is 90 degrees. So the magnitude of the cross product is 6 times the sine of 90 degrees, which is 6. Now, let's solve for the direction. Place your hand so it aligns with the first vector, g. Then, bend your fingers so they align with the second vector, h. Your thumb points along the positive z-axis. So the overall cross product, shown in red, has a length of 6 and points in the positive z-axis. Since we use the letter I hat to stand for the x-axis and j hat to stand for the y-axis, we can symbolize this product vector, which is in the z-axis, with k hat. So the shortest way to represent this cross product is 6k. Now, 2 observations are important about the cross product. First, the cross product vector is always oriented at right angles to both of the original vectors. That is important, and it will come up later. Second, in a cross product calculation, order matters. You will get the wrong answer if you reverse the order of the original 2 vectors. So it is important to respect which vector was first and which was second. Now, let's see a practical example, a proton in a magnetic field. The field has a strength of 10 to the negative 2 teslas and points in the positive x direction. Remember, only moving charged particles can feel magnetic forces. If the proton doesn't move, it feels no force. But that's not all. If the proton moves in line with the magnetic field, then the cross product ends up being 0, and the proton still feels no magnetic force. Likewise, if the proton moves exactly against the field, the cross product is once again 0, and again the proton feels no magnetic force. So, let's consider the case of a proton moving in the positive y direction at 500 meters per second. We can solve for v cross b like this. The magnitude of the cross product is equal to 500 times 10 to the power of negative 2 times the sine of the angle between the two vectors. Because the B field is aligned with the x-axis and the velocity is along the y-axis, the angle between these vectors is 90 degrees. Solving, the magnitude of the cross product is 5 Tesla meters per second. Now, the direction. Align your right hand along the direction of the velocity, positive y. Then, curl your fingers in the direction of the magnetic field, positive x. Then extend your thumb. The cross product points in the negative z direction. We can write this direction as negative k. So the overall cross product is negative 5k. For the last step, we multiply the cross product by the charge of the proton. That's 1.602 times 10 to the power of negative 19 coulombs. We get a force of 8.01 times 10 to the negative 19 newtons, and it's pointed in the negative z direction. Next, let's try a similar calculation with an electron. In this example, the electron is moving at 200 meters per second in the negative z direction. We'll keep the field at 10 to the negative 2 teslas in the positive x direction. We can see that the angle between the velocity and the magnetic field is still 90 degrees. First, find the magnitude of the cross product. 200 times 10 to the negative 2 times the sine of the angle between the two vectors, which is 90 degrees. The magnitude of the cross product is 2 Tesla meters per second. Next, find the direction with the right hand rule. Point your fingers in the direction of the velocity, that's negative z. Curl your fingers in the direction of the magnetic field, that's positive x. The direction of the cross product is negative y, also known as the negative j direction. So the overall cross product can be described as negative 2j Tesla meters per second. Finally, multiply the cross product by the charge of the electron. That's negative 1.602 times 10 to the negative 19 coulombs multiplied by negative 2j Tesla meters per second. That gives 3.204 times 10 to the power of negative 19j newtons. Notice that the negative signs cancel out and that the overall force is in the positive y direction. Even though the cross product points in negative y, the electron is pushed in positive y because it has a negative charge. Now, let's view the diagrams from our examples. Remember, the cross product is always at right angles to the two vectors it was based on. Because the force depends on a cross product calculation involving B, the force must be at right angles to the magnetic field. This is already different from electric fields. In electric fields, the force was aligned with the field. However, in a magnetic field, the force is at right angles to the field. And that's not even the most important part. According to this calculation, the force must also be at right angles to the velocity, always. What does this mean for the motion? Well, consider the analogy of a small planet moving around a very heavy star. The force the planet feels is towards the star, but its velocity is at right angles to the force. The force cannot alter the speed of the planet, only its direction of motion, and it keeps reorienting to stay at right angles to the velocity. The result is that the planet moves in uniform circular motion. More generally, Whenever the force stays at right angles to the velocity, the result is uniform circular motion. And that is exactly what magnetic fields do. Because the cross product causes the force to always be at right angles to velocity, the particle always moves in uniform circular motion. Since the particle is moving in circular motion, we should be able to determine the radius of the particle's orbit. I won't go over the full derivation, but it's not hard to do if you set the magnetic force equal to mass times acceleration, and then realize that centripetal acceleration equals v squared over r. A little rearrangement yields r equals mv over qb. This equation shows that the radius increases with the mass of the particle, but decreases with the charge of the particle. The bigger the mass, the bigger the radius. But the bigger the charge, the smaller the radius and the tighter the orbit. Also, the faster the particle, the bigger the radius. But the stronger the field, the smaller the radius and the tighter the orbit. We can see this in the following example. Here we see a beam of electrons subjected to a changing magnetic field. As the field goes stronger, the orbit of the electrons becomes tighter and tighter. At this point, we can round out our list of differences between electric and magnetic fields. In electric fields, the force is always in line with the field, but in magnetic fields, the force depends on a cross product that uses the field, so it is always at right angles to the field. Furthermore, in an electric field, the field is capable of speeding up or slowing down charged particles. But since the force in a magnetic field is always at right angles to the velocity, a magnetic field can only ever cause particles to move in circles at constant speed. Now that you've watched this video, you should understand how to find the force that a magnetic field exerts on a moving charge, how to calculate the radius of the orbit of that charge, and all the major ways that electric fields and magnetic fields differ.